Let's summarize a general procedure for selecting integration methods on the level of AP Calculus. So first we try the power rule if we have x to some power, and then we can try u-substitution, which applies if a function is a derivative of another. So in this case, cosine x is a derivative of sine x. And if we have a more complicated integral, we can try to apply some algebra to simplify it. So in this case, we'd multiply by 1 minus sine x on 1 minus sine x, and apply a trig identity to get the integral in a form where we can apply u-substitution. And if we have a rational polynomial function where the degree of the polynomial in the numerator is lower than that than the denominator, then we can apply partial fractions. And if we have some polynomial with a constant in the numerator, then we can complete the square to evaluate the integral using inverse trig functions. And polynomial long division applies to a rational polynomial function where the degree of the polynomial in the numerator is greater than or equal to that in the denominator. And we can apply trig substitution where we want to simplify the integral that has a radical in it, or a polynomial with x squared plus 1 and so on. And trig identities can be applied to simplify trig functions. So in this case, we'll apply the double angle trig identities to simplify this integral. And where we run out of options, we really apply dummy variables to simplify the integral. So here we have e to the power of x to the power of a third. And where we have the product of two functions that are different, or a single function that we can't evaluate using the above methods, then we can apply integration by parts. So post your thoughts in the comments of how you would actually apply these procedures. Let's evaluate this integral. So on first glance, you may want to use partial fractions because the degree of the polynomial in the numerator is lower than that in the denominator. But we can't really factorize the polynomial in the denominator, so we need to do a bit of algebra. So if we recognize that if we differentiate the polynomial in the denominator, we're going to get 2x plus 1, so we can somewhat apply u-substitution. So we have 2x plus 1 plus 4, and that's divided by the polynomial in the denominator. So we can rewrite the integral as follows. We can evaluate these integrals, and that's the same thing as evaluating this one. So the first one, we can use u-substitution, and in the second one, we'd complete the square and get an arctan. So what we can do is write x squared plus x plus 1 on 2 squared, and then 1/4 plus 3/4 is 1. So this can be written as x plus 1/2 all squared plus 3/4. And now you can evaluate this to an arctan using u-substitution and a bit of algebraic manipulation. And post your answer in the comments. Let's evaluate this integral. So what we'll do first is take the constant outside the integral, and we can apply trig identities to simplify this, but it's not quite there yet. So what we do is multiply by the conjugate in the numerator and the denominator. And therefore what we get is 1/2 by the integral of 1 minus sine x over 1 minus sine squared x, which using the trig identity gives cosine squared x. And now we can separate this integral into two, so we have 1/2 over 1 on cosine squared x, or sec squared x, minus 1/2 by the integral of sine x on cosine squared x. So to evaluate the second integral, we can apply u-substitution, and for the first integral, we can multiply it by 1 on sine squared x over 1 on sine squared x. So you'd get a cosec squared in the numerator and a cotangent squared in the denominator, and from that you can apply u-substitution and evaluate this integral. So post your answer in the comments. Let's evaluate this integral. So using a bit of algebra, we can write it as the integral of sine squared x by sine x integrated with respect to x. And we can further do a bit of manipulation. So using the trig identity, we have 1 minus cosine squared x by sine x dx. And let's further split this into two integrals. So we have the integral of sine x with respect to x minus the integral of cosine squared x by sine x dx. So this integral you can evaluate quite easily, so it's minus cosine x. And this one you can quickly evaluate using u-substitution. So post your answer in the comments. Let's evaluate this integral. So the functions here are derivatives of each other, so we can use u-substitution. So letting u equal sine x, du is cosine x dx. And therefore we can write this as the integral of u squared by du. So that evaluates to u cubed on 3, plus the constant of integration, and substituting for u, we get sine cubed x on 3 plus c. Let's evaluate this integral. So here we have two functions that are not the derivatives of each other, and we can't apply further algebraic simplification, so we're going to integrate by parts. And what I'm going to do is select u is equal to x squared to reduce the power of x. So what we get is du is 2x dx, and dv is equal to cosine 2x dx, and therefore v is equal to 1/2 by sine 2x. And multiplying u by v, we get x squared on 2 by sine 2x minus the integral of v multiplied by du. So the 2's are going to cancel and we get x by sine 2x dx. And now you can use integration by parts again to evaluate this integral, and then combine it with this result, add the constant of integration and post your answer in the comments. Let's evaluate this integral. So the indication is that the sine and cosine functions are derivatives of each other, so we can apply u-substitution if we do a bit of algebraic manipulation. So what we're going to do is use trig identities to write cosine cubed x as cosine squared x by cosine x. So cosine squared x is 1 minus sine squared x by the trig identity, and multiplied by cosine x integrated with respect to x. And now we can let u equal sine x, then du is cosine x dx. So we can write the integral as u squared by 1 minus u squared multiplied by du. And we can split this integral as the integral of u squared with respect to u minus the integral of u to the 4 with respect to u. And therefore this becomes u cubed on 3 minus u to the 5 on 5 by the power rule, plus the constant of integration, and then you can plug in for u and get your final result. This integral has functions that are not derivatives of each other, and it can't really be simplified algebraically, so we're going to apply integration by parts. And if we integrate either term, well, they're just going to go back and forth indefinitely. So what we'll do is just simply set u to either one of them. So u equals sine x, and du is thereby cosine x dx, and dv is e to the 3x dx, and therefore v is 1/3 e to the 3x. And we multiply u by v, so it'll be 1/3 e to the 3x sine x minus the integral of v du. And now we can apply integration by parts again in a similar way to evaluate this integral. And then the integral will be in the form of e to the 3x sine x. And then we set this result equal to the original integral, and then solve for this integral to obtain the final answer. So post your answer in the comments. Let's evaluate this integral. So sin x and cosine x are derivatives of each other, so we can use u-substitution. So setting u equal to sin x, du is cosine x dx. And therefore we can write the integral as u to the power of 32, integrated with respect to u. And therefore, using the power rule, we obtain u to the 33 on 33, plus the constant of integration, and then substituting back for sin x, we get sin x to the power of 33 on 33 plus c. Let's evaluate this integral of arcsine of x. Well, we know how to differentiate arcsine, so what I'm going to do is use integration by parts. So u equals arcsine x, and therefore du is 1 over the square root of 1 minus x squared dx. And therefore dv is dx, and v is equal to x. So we multiply u by v, which is x by arcsine of x, minus the integral of v multiplied by du, so that'll be x over the square root of 1 minus x squared dx. And now you can evaluate this second integral here by u-substitution and post your answer in the comments. We have an integral of a rational polynomial function with a higher degree polynomial in a denominator. So what we're going to do is use partial fractions, but first we need to factorize the denominator. So we can write 8 as 2 cubed, and now we can use cubic factorization to factorize the cubic. So I have x minus 2 multiplied by x squared plus 2 by 1 by x, and then plus 2 squared, which is 4. And now we can write this in partial fraction form. So we have a linear factor, and then plus the irreducible polynomial. So we plus bx plus c on x squared plus 2x plus 4. And now you can apply your usual method of partial fractions to obtain these coefficients and evaluate the integral and post your answer in the comments. Let's evaluate this integral of a rational polynomial function with a higher degree polynomial in a denominator. So we'll use partial fractions and take the constant outside the integral first. So inside the integral, we need to factorize the denominator. So we have 2x squared plus 5x minus 1. And we're going to use cubic factorization to factorize this cubic. So we'll write the 1 as 1 cubed. So we have x minus 1 multiplied by x squared plus 1 multiplied by the coefficient of x multiplied by x, and then plus 1. And now we can equate this with some constant over this linear factor, and then plus bx plus c on this irreducible polynomial. And now you can apply your usual method of partial fractions to obtain these constants, then evaluate the integral and post your answer in the comments. Let's evaluate this integral with the same degree polynomial in the numerator and the denominator. So we can apply polynomial long division. We'll just use some simple algebra first. So we have 2 plus x squared, and then subtract the 2, and we don't alter the integral. So now we can write this as the integral of 2 plus x squared on 2 plus x squared, which is 1, evaluated over x, and then minus the integral of 2 on 2 plus x squared, integrated with respect to x. So this can be evaluated quite easily, and this integral is going to evaluate to an arctan. So have a go at doing this, and post your answer in the comments. Let's evaluate this integral. So our option is to use integration by parts, because we know how to differentiate arcsec. And du is equal to 1 over the absolute value of x by the square root of x squared minus 1 dx, where x is going to be greater than 1. and therefore dv is dx, and v is equal to x, and therefore we can write the integral as x by the arcsec of x minus the integral of v du. So x is going to cancel, so what we get is 1 over the square root of x squared minus 1 dx. And now you can evaluate this integral using trig substitution, and have a go at doing that and post your answer in the comments. Let's evaluate this integral. So what we're going to do is apply integration by parts, because we know how to differentiate arctan. So du is equal to 1 over 1 plus x squared dx. And therefore dv is dx, and v is equal to x. So we can write the integral as u multiplied by v, so that'll be x by the arctan of x, minus the integral of v du. So it'll be x on 1 plus x squared dx. And now you can evaluate this integral using u-substitution, and post your answer in the comments. Let's evaluate this integral. So first we're going to apply trig identities to simplify the cosine. So we have sine x to the power of 100 by cosine squared x by cosine squared x by cosine x dx. And now we can use trig identities. So we have sine x to the 100 multiplied by 1 minus sine squared x. So that's cosine squared x, and we square that by cosine x dx. And now you can easily apply u-substitution to evaluate this integral and post your answer in the comments. Let's evaluate the integral of sec x. And if you tried integration by parts, you're going to make the integral worse, because the derivative of sec x is equal to sec x tan x. And we also know that the derivative of tan x is sec squared x. So what we're going to do is try to get this in a form where we can use u-substitution. So we can add these together and write sec x multiplied by tan x plus sec x. And to leave this integral unaltered, we're going to divide through by tan x plus sec x. And this is integrated over x. And now if you set u equal to tan x plus sec x, then du is sec squared x plus sec x tan x. And now you'll be able to easily evaluate this integral by completing the u-substitution. Let's evaluate the integral of sec x to the power of 4. And because it's an even power, we can write this as sec squared x by sec squared x dx and use a trig identity. And dividing through by cosine squared x, we get 1 plus tan squared x is equal to sec squared x. And therefore we can write the integral of sec squared x by 1 plus tan squared x over x, and therefore we can set u equal to tan x, then du is sec squared x dx, and now you can write the integral of 1 plus u squared with respect to u, and you can complete the u-substitution now quite easily. Let's evaluate this integral. So here we're going to use integration by parts. So u is equal to the natural log of 3x squared plus 1. Then du is equal to 6x on 3x squared plus 1 using the chain rule. And therefore dv is dx and v is equal to x. So we have u multiplied by v minus the integral of v du. Now what we can do is take 2 outside the integral. So we end up with 3 here. And now you can do a bit of algebra by adding 1 and subtracting 1. And what you'll get is this integral in the following form. So you'll have 2 by the integral over x, and then minus the integral of 1 on 3x squared plus 1. And you could have obtained this using polynomial long division also. So you can evaluate this one quite easily, and this integral here evaluates to 1 arctan. So have a go at evaluating this, and then combine it with this result and post your answer in the comments. Let's evaluate this integral. So if we use integration by parts, this integral is going to get more messy, because the derivative of cosec x is equal to minus the cotangent of x by cosec x. And we also know that the derivative of the cotangent of x is minus cosec squared x. So therefore we can rewrite this integral by factoring out cosec x and adding these two derivatives together. So what we get is minus outside, and we have cotangent of x plus cosec x. And to leave this integral unchanged, we need to divide through by minus the cotangent of x minus cosec x. So in other words, this minus is going to cancel. And now we can use u-substitution by setting u equal to the cotangent of x plus cosec x, and therefore du is minus cosec squared x minus cosec x by the cotangent of x. And now you can easily complete the u-substitution and post your answer in the comments. Let's evaluate this integral. So because it's an odd power, we need to rewrite the integral as cosec squared x by cosec x dx and use integration by parts. So we have u is equal to cosec x, then du is minus cosec x by the cotangent of x dx, and dv is cosec squared x dx, and therefore v is equal to minus the cotangent of x. So u multiplied by v gives us minus cosec x by the cotangent of x minus the integral of v du. So that will be cosec x by cotangent squared x. And now we can apply our trig identity. So if we divide through by sine squared x, well, what we get is the cotangent squared x plus 1 is equal to cosec squared x. And now we can make our substitution for cotangent squared x. So we get the integral of cosec x by cosec squared x minus 1. So effectively we've replaced this integral, and then we just subtract the result from here, and then equate the result with this original integral and solve for the integral of cosec cubed x. So have a go at doing that and post your answer in the comments. Let's evaluate this integral. So to do that, we're going to use trig substitution. So we have our typical trig identity, and we're going to set x equal to sine theta. So therefore dx is cosine theta d theta. And now we can substitute for x in the integral. So we have sine squared theta by dx, which is cosine theta d theta. And the square root of 1 minus x squared is the same thing as the square root of 1 minus sine squared theta. So what we have is the square root of cosine squared theta, which is cosine theta. And the cosine thetas cancel, and you can replace sine theta with the double angle trig identity. So 1/2 minus 1/2 cosine 2 theta d theta. And now evaluate this integral, sub back for theta, and you'll get your answer in terms of x. And post your answer in the comments. Let's evaluate this integral. So here we can apply the double angle trig identities. So 1/2 minus 1/2 cosine 2 theta. So that will be 6x, and that's multiplied by 1/2 plus 1/2 cosine 2 theta. And we're integrating with respect to x. So we can expand and simplify. So we have 1/4 minus 1/4 cosine 6x squared, integrated with respect to x. And now you can apply the double angle trig identity again, and evaluate the integral and post your answer in the comments. Let's evaluate this integral. So what we'll do is use our typical trig identity. And to get this in the form of 1 plus x squared, we're going to divide by cosine squared theta. And we'll set x is equal to tan theta. And therefore dx is sec squared theta d theta. And substituting for dx, we get sec squared theta d theta. And substituting for x squared gives 1 plus tan squared theta, which is sec squared theta to the 5/2, or sec theta to the power of 5. So this simplifies to 1 over sec cubed theta, which is the same thing as cosine cubed theta, or cosine squared theta by cosine theta d theta. And now you can substitute for cosine squared theta using this trig identity, and then use u-substitution to evaluate the integral. Substitute back for theta and post your answer in the comments. Let's evaluate this integral. So applying integration by parts is going to make this more difficult to evaluate. So what we'll do is use dummy variables. So I'm going to set w is equal to e to the power of x to the third. And if we take the natural log of both sides, we obtain x to the third, and then cube both sides, we get x is equal to the natural log of the dummy variable w cubed. And therefore dx is equal to 3u squared by du dx, which is w in the denominator, using the chain rule. And we evaluated this with respect to w. And now we can substitute for e to the power of x to the third, so that's w. And dx is 3 on w by the natural log of w squared. And this cancels, and now you can use integration by parts. And we've evaluated the integral of the natural log previously, which you can use here. And then after you evaluated the integral, you can sub back for w and get your answer in terms of x. And post your answer in the comments. We have the integral of the product of two functions, so we'll use integration by parts. And we don't want to integrate arc cotangent, so we're going to set it to u so we can differentiate it. And we know the derivative is minus 1 on 1 plus x squared dx. And dv is x squared dx, and therefore v is equal to x cubed on 3. And then multiplying u by v, we have x cubed on 3 by the arc cotangent of x minus the integral of v du. So minus minus is a plus, and we take 1/3 outside the integral, and x cubed on 1 plus x squared dx. And now the degree of the polynomial in the numerator is greater than that in the denominator, so you can use polynomial long division to evaluate this integral, and post your answer in the comments. Let's evaluate this integral, which looks a bit tricky to apply integration by parts. So we'll try to put it in a form where we can apply u-substitution. So what I'm going to do is just multiply by e to the x on e to the x, and we don't alter the integral this way. So if we take the 4 outside the integral, so we have e to the x in the numerator, and then e to the minus x by e to the x is 1, plus 3e to the x, integrated with respect to x. And now we can set u equal to 1 plus 3e to the x, and therefore du is 3e to the x dx, and this integral becomes 4 by the integral of 1/3 du, so divide by 3, and then in the denominator we have u. So that's equal to 4/3 by the natural log of u, which is 1 plus 3e to the x plus the constant of integration. Let's evaluate this integral. So the degree of the polynomial in the numerator is lower than that in the denominator, but we need to factorize the denominator to use partial fractions. So to do that, we'll use the difference of squares. So x squared minus 1 by x squared plus 1. And we can further factorize the first factor. So what we have is x minus 1 by x plus 1 by x squared plus 1. And now we can apply partial fractions. So for the linear factors, we have a constant a and a constant b. And for the irreducible quadratic, we have a constant c by x plus another constant d on x squared plus 1. And now you can multiply through by the denominator and use a typical method of partial fractions to obtain these constants. And the integral then becomes a lot easier to evaluate in this form.